Thank you very much for the invitation, for all words which were said, and for the possibility to talk about the origin of deterministic chaos. Before I begin, I would like to thank many people who are here. Just first of all, our lecturers today, Professors Margulis, Khanin, and Sas, and also my first students, Grigorevich and Ratner from Russia, and Jonathan Mattingly, if he is here, from the United States. And also I have some affiliation in Moscow and some affiliation in Princeton, and I would like to thank two of my bosses who just found it possible to come here and to participate in this meeting, namely Professor David Gabay and Professor Kuleshov. So now just I would like to come closer to the topic of my talk. I already had a chance to say that there exist two different words, disorder and chaos. So if you enter a room where just everything is in some just random sequence, then it is disorder. For example, if your wife or somebody just scolds you, then she scolds you for disorder, but not for chaos. Yeah, so, but chaos differs from disorder by the fact that chaos always requires something developing in time. So you can just say that, you cannot say that chaos is just at one place. Chaos is characterization of some evolutions. And so the purpose of my talk is really to explain how the notion of deterministic chaos appears, what does it really mean, and I want to explain to you concrete problems which just people solve in connection with this theory. Sometimes people ask me, who just told you that you should work on the problem of deterministic chaos? The answer to this very important question is unfortunately negative. Nobody told me that. And the reason is the following, that the words deterministic chaos appeared much later than the works on deterministic chaos were done. But people who were working in this field did not know that they work on chaos. In just old times, it was called maybe the works on ergodic theory, or some people say dynamical system, but for physicists it was not satisfactory. They wanted to have really some special words. And three physicists, Chirikov from Russia, Joe Ford from the United States, and George Zaslavsky, also from Russia, proposed this word deterministic chaos. However, if you talk to some people, they will tell you differently, because there was a paper by two mathematicians, Lasota and Yorke, which was called Period 3 Implies Chaos. I don't want to discuss what was actually in that paper, but some people say that the origin of chaos appeared after the works of Lasota and Yorke. Actually, it does not matter, so, but now just the words deterministic chaos are used practically everywhere. And so the purpose of my talk is really to explain what does it mean deterministic chaos, what are the problems which appear while people study deterministic chaos, and what are some results. So sometimes people say about deterministic chaos that it is randomness of non-random. So randomness is something what is studied in probability theory. In probability theory, when we have coin tossing or something like this, we can just take a coin and flip it, say, 1,000 times, then forget the results, flip it again, and so on, and just accumulate somehow statistics. In the theory of deterministic chaos, we don't have so much of freedom. We can consider only one trajectory or one sequence of numbers. And the problem of chaos is just looking at this single trajectory to say in what sense it is random. So these problems appear quite often in number theory. So number theory is connected with single sequence of prime numbers. We cannot change the sequence, and we want to know statistical properties of many objects which are defined with the help of this prime number. Therefore, just one can say, but it's my point of view, other people will not like it, that number theory, in a sense, is a part of deterministic chaos because of that property. So what does it mean non-random? Non-random just means that we consider system of ordinary differential equations, which are written, I hope, on the screen, or maybe even one step before. So just, I probably did something with the technique. Yeah, this one? Yeah, okay. No, just... Yes, so the main object with which people are dealing with is solutions of system of ordinary differential equations, but this actually means, first of all, that we can consider infinite dimensional system where we have infinitely many unknowns like xj, and the right-hand side, if I can be more or less arbitrary. So we can consider the system of equations 1 or 2 as equation which just determine some evolution in time. So the theory of deterministic chaos just studies all possible process of evolution. In this sense, deterministic chaos can have possible applications in biology, in physics, and in many other fields. So we don't specify any, so far we don't specify any special properties of these equations. Then just comes the next very important question, which we should have in mind. So what does it mean? What does it mean that solution of ordinary differential equation, which does not have any randomness in the right-hand side, no random noise or the random terms, has statistical properties? Now, this is just question in mathematics, not just in applications. And there is just some way to describe statistical properties. And the first statistical property is the existence of time averages, which are written here. Just one of the examples for this is just the following. Suppose that we measure in Oslo the temperatures each day, and we have just a measurement, for example, during the whole year. Then it is just a sequence of numbers, and when we consider time averages, then we have the average temperature in Oslo. But the question to mathematicians is the following. What will happen if we measure this temperature not 1 year, but 10 years, and will the result be the same? The question to mathematicians is the following. Definitely we would like to be it the same, But then what are the property of system of equation of dynamics which somehow stabilize time averages? So, as I already said, this time averages always exist in probability theory, and there are the laws of large numbers which say that this time averages exist with probability just approaching to 1. But again, in the theory of deterministic case, we cannot use probability theory because we have only single trajectory. And then the question is, why single trajectory is random, and in what sense? So now we shall make a step which is, then we make a step which just for people far from this field can consider artificial or difficult, but without this step we cannot say anything. We assume that there exists some just distribution in the phase space of our dynamics, which in principle determines the values of all time averages, about which we still don't know anything. The exact formulation is the following. Let's consider time averages, which is written on the blackboard like the integral of the f of xt, rho of x d of x, and we want to find such function rho of x when this integral does not depend on time. And later there will be the theorems which explain why a function rho with this property is responsible for the appearance in the values of all time densities. The interpretation of the functions rho which satisfy this property are called invariant density, and there is just picture which you might not like, which explains what is the meaning of this function rho. The meaning is just the following. If you consider the measurement at t equal to 0, then you have should try to use both. Okay, then you have this integral, and then you consider a similar integral for any values of time. But if the function phi, you consider the argument x minus t. It means that the value of our initial point at the moment of time minus t. And then the invariance means that these two integrals should coincide. And then we use just the first highly non-trivial theorem in mathematics, which says that as soon as we have this measure, then time averages exist. In other words, if we, in the presence of stationary measure, we can take time averages just for any values of time, for example, from 1 year, from 0 to 1 year, from 1 year to 2 years, and so on. And time averages will exist, and they will not depend on time. The problem of existence of such stationary distribution is a very just well-known problem in all this field, but now I shall not discuss it here because it will lead us slightly to something like a wrong direction. We assume that this way of measuring the densities, the averages exist, and we shall use it, but we shall not discuss the origin of it. How does it appear? It is some property of equation of motion which are valid in many cases, and just from the point of view of applications, it means that there exists stationary regime. So in other words, we assume that time averages of the temperature during 1 year are more or less just the same for each year, but we don't know their value. Then the next property which I want to discuss is called mixing. It's certainly connected with mixing of different kinds of liquids in a glass. And it was introduced, so there were, no, I'm sorry, I want to explain two notions which were introduced by two great physicists in the beginning of the 20th century, Ludwig Boltzmann and Josiah Gibbs. Boltzmann lived in Austria, Gibbs lived in the United States. Once Boltzmann visited the United States, but their trajectory did not intersect. Yes, so they never saw each other and never talked. Nevertheless, each of them made just a very important contribution to our field because they introduced the concepts which play the central role. And so, so Boltzmann introduced the notion of ergodicity. Ergodicity means that the time averages are exactly the values of the integral, which is just written there, just the integral f of x, rho of x, d of x. And I just like very much to illustrate the notion of ergodicity on the following example. Suppose that you decide to buy a pair of shoes or something else, and you live in a house which on the first floor has a shop selling the shoes. In this situation, there are two strategies. One strategy is just the following, that you just go down, to look at the shoes, and take the best one, which is just good for you. Another strategy is the following. You take your car and go along all stores in the town and find the best shoes there. The system is ergodic if the result will be the same. In other words, you can just try to find the shoes during one trip in the town, or you can just check the shoes in your store, say, during 1 month, and also choose the same. So the popular formulation of the property of ergodicity is the following, that time averages coincide with space averages. Time averages, it's what you are doing when you just go to this shop every day during some interval of time. And space averages is property when you go with your car along some space, along the town where you are. And the results are the same. Yeah. This property is valid in certainly much more complicated situation where you have the equation of motion. One can formulate it in precise way, but this is just some approximate formulation. Then we also need the property of mixing, and the property of mixing is something which is very important for all these kinds of dynamics, and it just says the following. If we start initially with some domain in the phase space, which has a nice form, some like round form, and consider its dynamics, so its evolution after time t, then what will happen during the dynamics with mixing is that everything which has a nice form with increase of time becomes so ugly that we cannot distinguish the part of the space where we were at t equal to 0 from the part of the space which comes there during the result of the dynamics. And this property of mixing plays an important role in studying statistical properties of our dynamics. Its precise formulation, is just the one which I explained it before. And the last property is the so-called Gaussian distribution for fluctuations. fluctuations are just the expressions which show the deviation of time averages from the space averages, if this is written here. And as in the usual probability theory, we would like to know whether whether these differences have Gaussian distribution. But it's not Gaussian distribution which we have just in the theory of hazards or just card games and all others, which just led to the origin of probability theory, because it is Gaussian distribution for dynamics where we have no randomness at all. So it should be the property of dynamics. And in this sense, it is a different statement. So let me summarize what I said so far. So we have this property like ergodicity, mixing, central limit theorem. And then we have our system of equation. And we want to know when the dynamics described our system of equation and just has the property which are written here. And it was a great surprise when at some moment of time it was discovered that this property of randomness, the ones which I mentioned, can be without any random mechanism, without anything just where we, the results are just based on the property of something like tossing or just card games and something like this. So the discovery of this property was connected with the concept of ergodicity, with the concept of entropy, which appeared in dynamics. Entropy is just a very well-known object in statistical physics. And it started to play a much bigger role in connection with information theory, developed by Claude Shannon. And then I want to make some remark. Several years ago, I met with a famous mathematician, Kakutani, who was a great just expert in the theory of dynamical systems. And he told me that he was very much connected with John von Neumann, and he and von Neumann discussed the possibility of using entropy in dynamics. And nothing was published, and I tried to convince Kakutani that it's necessary really to explain just openly what was discussed there, but this did not happen. And the great progress in this field appeared after the work of Kolmogorov. After the work of Kolmogorov in 1959, when he introduced the notion of entropy in dynamics. So in thermodynamics, in statistical physics, the entropy somehow measures the size of the phase space. For example, if we consider the system of statistical mechanics in this room, then the entropy measures how many possible trajectories of molecules of gas are possible, and something like this. As you will see, similar role by entropy is played by entropy in pure dynamics. So I want to give you one example, but this example requires a little bit of mathematical construction. It is just the following. Denote the space of our dynamics by omega capital, and omega capital is a standard notation in this theory, as in probability theory. So if you see a paper where you have a letter omega, then with high probability, this paper will be about deterministic chaos or probability theory. So just when we have this space omega, then the next property which we can have is to decompose it onto some subsets. What is the meaning of these subsets? Suppose that we make some measurement of dynamics. Then it is difficult to measure exactly the position of moving point. What we can do is just to make more crude just measurement, namely for each moment of time, we measure only the element of our subset omega sub j in which the point is. So so more precisely for the point x, we write the sequence of symbols, and this writing means that at the moment of time k, the point x of k belongs to subset number k. And then we consider a rather complicated expression, but actually not so bad, which is just minus 1 over n. Minus just is usual sign in this field. If you study some question in statistical mechanics, they always have the sign minus much more often than plus. So it is minus 1 over n, and then the sum of logarithm of probability of trajectories, which is with given evolution in time. And then times probability itself. So this writing already shows that we just assume that there are so many possible trajectories of dynamics, then these probabilities P are non-zero, and therefore the whole sum has some meaning. Yeah. And then it is a general theorem, which whose proof is even not so just difficult, which says that there exists the limit of this expression as n tends to infinity. So if we look more attentively to the formula 5, then it actually means that we make the summation over all just possible evolution of our dynamical system. And then the entropy, which is written here, takes only a non-negative value. And the entropy of dynamics, if we want to have a number which does not depend on the partition of the volume onto some initial part, then it is just supremum of all this expression over all possible means of measurement. And then when the entropy appeared, then there was just a clear feeling that the entropy can allow us to distinguish dynamical systems which appear in probability theory from dynamical systems which appear in deterministic equation or equation of evolution, which I wrote before. In other words, there are two classes which are somehow non-overlap. It turned out that this was not the case. It was somehow the evolution of science, not somebody's just surmise, but it turns out that the logic which follows from all this natural definition shows that there can be just types of dynamics for which this limits the entropy can just be positive even in the system of even the systems which are determined by the equation of evolution. The most important example is the so-called Arnold cats, after the paper of Arnold where he just reproduced the form of the cat after the dynamics in very just chaotic system, which is very much different from the initial form of the cat. So even difficult to say that this is a cat. Therefore, this is the reason why it is called Arnold's cat. But I can tell you that Arnold never had a cat at home. He had only dogs. So then just so it just example showed that there are deterministic system without any randomness for which the entropy takes positive values, exactly like in the case of this dynamical system or evolution appearing in probability theory. So it means that from the point of view of deterministic chaos, we cannot really distinguish the system in probability theory from the system in pure dynamics. And then there was just a general question, how can we describe deterministic system without any randomness which have positive entropy? In other words, which demonstrate some property of evolution which we know quite well in probability theory. And then there comes a very important statement which just says the following, that in order for just deterministic dynamical system have positive entropy, it is necessary that the dynamics which is described by this equation were unstable. So randomness follows from instability. This was very important conclusion, and just the first, as far as I know, the first person who somehow just wrote about this possibility was Poincaré, who just described in his textbook on probability theory the following picture for random events. Suppose that we have just a pendulum in the position of unstable direction, and then the question is where we would move, to the right or to the left? And this is a very difficult question because the answer depends on fluctuation of the air in the neighborhood of this pendulum, and people prefer to say that probability 1/2 it goes to the right, with probability 1/2 it goes to the left. But now we would describe this phenomena in a slightly different way. We have a dynamical system, and we can perturb a little bit initial condition, so it will go to the right or it will go to the left. And this is exactly the instability which we need. Again, let me stress that we don't have any just additional terms like noise and so on. So how to study these properties of instability? So in order to do this, we must consider what is called the theory of small perturbation or linear perturbation of any deterministic dynamics. If we have the system of equations, which I wrote before, then we can consider initial conditions. But how can I use it as a pointer? No, okay, doesn't matter. Yeah. So just we can linearize our nonlinear system around any particular solution of nonlinear system, and then we shall have a linear system, which is number 6 in this form, in this page, with coefficient depending on time. Okay, good. With the coefficients depending on time. Therefore, it is a linear system with time-dependent coefficients. And it is well known that linear systems which are time-dependent can be as complicated as nonlinear systems. Okay. Oh, thank you very much. Can be as complicated as just nonlinear system. And for example, initial point x0, or the trajectory x0 of t, is called unstable, and for some initial conditions, solutions of the equation 6 grow exponentially with time. again, let me stress that it is property of the system, and it is not. It does not follow from of some additional just assumptions. And then it is important to study the set of all possible solutions of x of t and to find which of them are unstable, like it is here, and which are stable. Stable are solutions z of t, which tends to 0 exponentially. And there is a very important paper by the Russian mathematician Asiledets, which just prove general theorem, which just describe all possibilities which can happen in this case. I'm sorry. There are only two. Which can happen in this case. And so, generically, so if we look at the solutions, then there are initial conditions for which solutions grow exponentially with time, and solutions which decay exponentially with time. Do you agree with this statement? Yeah, no, you should not agree, because there can be solutions which do not grow. But this is the case which we don't discuss now. We want to consider just typical case when there are only growing or decreasing solutions. And we denote by nu of s and nu of u the number of exponentially growing or exponentially decreasing solutions. The letters s of u were proposed by great American mathematician Steve Smale. The letter S means stability, and U means instability, and nu of S is the number of solutions which just decay, and nu of U describes the number of solutions which grow. And then a big role in the theory is played by the so-called Hadamard-Perron theorem. Hadamard-Perron theorem says that when we have the number of stable solution k and the number of unstable solution L, then typically, or at least it is just the property which can be easily checked in various cases, then these numbers do not depend on the initial condition, and when they exist, then the structure of solutions near the trajectory x0 of t is very simple. So initially we have our point x0, where it is drawn here. So it goes from minus infinity to plus infinity in time. And then there can be solutions which have the following remarkable property. If we solve our system of linear equation for this initial condition, then the solution for this initial point and this initial point will differ by a number which tends to 0 exponentially. So these are very special initial conditions, and in Hadamard-Perron theorem, there is the whole local submanifold where this property holds. And then there is unstable submanifold gamma u of x0, which is as shown here. And it consists of trajectories so that we have exponential convergence when time tends to minus infinity. In other words, if we follow solution very far to the left, then they will differ from solutions to our initial point x0 exponentially fast. So this is a very important theorem. This is a very important theorem which has many applications and modifications, and I hope even to be able to show you some cases where this theorem implies some property which you will not know if you not study the theory of deterministic chaos. So just Yeah, here it exactly is. So let me just give you some definition. So I want to consider the system which is called Anosov system, after a Russian mathematician Anosov, which just is the following, that the system is called Anosov system if for each initial condition it has local submanifolds gamma S, gamma of U, which is locally are smooth, and the angle between this submanifold at any initial point is strictly positive. So you should not think about this definition. I shall simply give you some number of examples. The main example of Anosov system is the so-called dynamics on a compact manifold of negative curvature. So this case of dynamical system is very important for different parts of mathematics, like representation theory, all that. And it shows that the theory of deterministic chaos is very much connected with so-called hyperbolic manifolds, where we have stable and unstable solution of our equation. So the examples of this system can be found among billiards. The billiards will be discussed in the talk by Domokos Sas. I want to give you only some examples of this billiard system. So this is just a domain with concave boundary, and this is another domain, which is the square from which a circle is removed. And the basic property of both examples is just the fact that the boundary is concave. If you just orient the boundary so that normal vector are directed inwards. Then there is another example which plays very important role in the theory of deterministic chaos, which is called Bunimovich stadium. And it is just a very special case when a mathematician has his own stadium. And so the stadium is a domain where the boundary consists of two straight lines and two semicircles. It is very important that there are points where just the angle between this part of the boundary is non-zero. There are some generalization of this example, but if you see this for the first time, it is important to see that there is a presence of this singularity. And we consider the stadium, and the fact which follows from deterministic case and which is practically not known to geometry is the following, that if we just start from arbitrary point x, to take this initial condition, and then there exists a curve, and then for this curve we can consider its normal at each point, and if we consider solutions of our equation of linear perturbation, or if we just consider geodesics or trajectories which go out from the point of this curve, then this trajectory will converge to each other exponentially fast, but will never intersect. This is just very special property, and for us it is especially important. So then I want to mention to you this famous Lorenz system. Lorenz was just a great expert in just geophysics and meteorology, and he just wrote down this system of three ordinary equations with some constant coefficients, sigma, r, and b. And he studied the property of some convections. And I just am giving to you an example of this system in order to show to you that the theory of deterministic chaos can be connected with very just concrete systems of equations. So it's not so abstract, which you might think from the very beginning. And so here is just a picture which somehow demonstrates the property of solution to this system. It has just two very special points, or two special domains, here and here. And the trajectory of this system just go from one half of this space to another half. And so what is the property of deterministic chaos which we have in this case? Suppose that you write to me a sequence of numbers, R and L. Right means right, and left means right is right, left means left. Yeah. And then if you give me this sequence of symbols, then it is possible to find a trajectory which goes from the left part to the right part according to this sequence of symbols. So in this sense, if you consider this sequence of symbol, it is a random sequence, because typical sequence of signs is always random. But on the other hand, it is a solution of our system of equations where there is no randomness. So this Lorenz system was very important, but the fact which is connected with this system was the following, that it was published in 1962 when the theory of deterministic chaos was at the very beginning. And it was published in a journal of, I think, meteorological science or something like this. And neither mathematician nor physicist practically read this journal. Therefore, the paper by Lorenz stayed unnoticed for something like 15 years. And after 15 years, it became extremely popular. And one of the rows which was connected, or the hopes which was connected with the system, was the following, that maybe it is connected with the famous phenomenon of turbulence. In other words, turbulent motion in the fluids behave in a sense as solution of the Lorenz system, or just better to say that Lorenz system can be considered as an example of the onset of turbulence. So there was later famous paper by David Ruel and Florence Takens, which was called The Nature of Turbulence. In this system, the equation of fluid dynamics never appeared, never were written, but the basic idea of this paper was the following, that maybe turbulence is connected with the presence of so-called strange attractor or invariant sets of our dynamics, which in a sense behave as solutions of the Lorenz system. I shall not discuss today how far this hypothesis did go, but it certainly played a very important role in the whole theory. So I think I must finish quite soon. I shall skip some number of pages. I certainly could say more about statistical properties which were discussed. I want to give you only the portrait of several great mathematicians whose work played an important role in the whole theory, and that will be the end of my talk. So this is the portrait of von Neumann, who just actually started with a class of dynamical system with pure point spectrum, where there is no randomness, but dynamics is described by quasi-periodic function. This is a portrait of Eberhard Hopf, who just studied the dynamics in the spaces of negative curvature. Then These are 3 portraits of Kolmogorov. He just made several contributions to the series, therefore he has 3 portraits, but it's the same person. Then Smeo just worked in the topological theory of dynamical systems, which is certainly just a close relative of deterministic chaos, and their school and our school somehow uses more or less the same object and tries to prove very close property. This is the portrait of Anosov. Then this is David Ruel. I never saw David Ruel with a bird, but probably it was because the photograph exists. Yeah. This is a portrait of Pesin, who just proved important theorem in this hyperbolic dynamics. This is the portrait of, the portrait of Lorenz, and then the portrait of Bunimovich, and this is Mitchell Feigenbaum, who's just, he just had fantastic results in the theory of dynamical systems. I did not have time to discuss his result. I just, in this connection, I want only to stress that the development of the theory of dynamical system was just like a sequence of breakthrough, separated by periods of rather latent or slow development. So one of these breakthroughs is connected with the name of Mitchell Feigenbaum. This is Michael Benedicts and Leonard Carlson, whom I think many of you know. And then the last phrase is that the modern theory of deterministic chaos is oriented towards new applications, especially in fluid dynamics, and I think maybe such general problems and problems of climate and changes in the atmosphere and all that, but I cannot say anything about this, so I must stop. Thank you very much.